All right. Hello, good morning, good day, good afternoon. Welcome, physics students, to Newton's Laws of Motion, number 2. Today we're going to be doing some problem solving. So in our last lesson, we talked about Newton's Laws of Motion and then had you doing some free body diagrams. So, if we could sort of summarize the laws of motion, the first law of motion being the idea of inertia, that objects at rest remain at rest, and that objects in motion remain in motion, traveling in a straight line. The idea of objects at rest, that's pretty easy for us to know and recognize, and we see it all the time. The dirty clothes in your room remain at rest on your floor. At least I've seen that for my sons. Or the coffee table stays at rest in the living room. It doesn't move on its own. The hard part is when objects are in motion and they stay in motion, traveling in a straight line. Because we don't often see that. We don't often see that because friction is real, and friction is always there, sort of interrupting what we're trying to do. So friction tends to take away from the idea that things continue in motion. The only thing I can think of, if there was a car rolling, it takes a lot of effort to stop it rolling, just like it takes a lot of effort to get it rolling. The Newton's second law is that when there is a force that is applied to an object, that can cause an acceleration of the object. And so here, it's important to recognize we're talking about the net force. Because you might just say, well, sir, I went to my bedroom and I pushed against the wall, and I pushed, and there was a big force that I was doing at. Like, it was a big force. Did I say a big force? I mean, it was a big force. But my house wasn't accelerating. So there. But you have to remember that if you're pushing with a force in this direction, what you're also getting is a force in the opposite direction from the house. If this was you pushing with that force, this is the house pushing with that force. And if those two forces are the same, there will be no acceleration. And our net force then would be equal to 0. Okay. We'll talk more about this, but just recognize. And so where did this force of the house come from? Well, it comes from Newton's third law. For reaction, there's an equal and opposite reaction. Forces don't really occur just by themselves. When you punch someone, your hand feels the punch as much as they felt your hand. All right, inertia. This is a fellow named Steve Spangler. And if we were in class, I would probably set something up like this as well on the table at the front. I've got a piece of cloth. It's an old flour bag piece of cloth. And I've got some things I've put out onto there. And then I'm sure you've seen it, where the person who does this gives a sharp tug on the tablecloth. And these objects remain where they are. And the tablecloth comes out, and they're just sort of sitting there. And if it's done right, hey, it's done right and it works well. And if it's done wrong, hey, things go flying in different directions. The salt spills, the water spills, the plates and bowls crack and chip. The trick, you can really see this, what Steve is doing, is that when he's pulling, he's not pulling straight out, he's pulling down. And so that keeps the tablecloth coming down and low underneath that. If you tended to pull out, you might tend to pull up a bit, and that gives the objects on the tablecloth some upwards force that causes them to go flying. Now, your mom might have some nice china. Well, don't use the china. Or she might be some nice crystal glasses and so on. Don't use the crystal glasses. Use plastic. Use your plastic stuff if you're wanting to try this at home so you don't break things. And don't do it near stuff that's breakable either. Don't get me in trouble. All right. So let's just talk about some examples of, sort of some questions, because Newton's three laws of motion that I've tried to put out to you is sort of a way at uh, of looking at the world, and that's where free body diagrams come in. Is that the free body diagrams are having us take a look at the world, to take a look at the forces and so on that are happening. Okay, so here we have a jet. So first of all, what we should do is draw a picture of a jet, and there's our picture of a jet, and is traveling at a constant speed. Well, constant speed means the acceleration is equal to 0. And if we want to take a look at this, we know F net is equal to ma. And so we can say, well, a jet plane, if the acceleration is equal to 0, what's the net force going to be? And so if we have our mass times 0, well, our net force is going to be equal to 0, because anything times 0 is equal to 0. Could the mass be equal to 0? Well, yeah, but then it's kind of pointless as well. If something has no mass and is accelerating, there's still no force on it. But to accelerate nothing doesn't mean much. All right, so we've got a jet plane, and it's traveling at a constant speed and in a straight line. So what we're going to have is a force of gravity. We always have the force of gravity. Well, there's always force of gravity. Why is there always a force of gravity? They're weightless in space. In space, when they're in orbit, they are falling. They're constantly falling. They're falling around the Earth, or if they're going towards the moon, they're falling towards the moon. They're always falling, and they're falling towards this net gravity that's happening. All right, so we'll have gravity. And so it's a jet plane. Is it on the ground? No. Is there a normal force? No, because there's no surface. But what we have is a force aerodynamic. You can think of the interaction of the wings with the air, and that gives an upwards force. If those wings fell off, what's going to happen? It's going to accelerate towards the ground, and it's going to crash. So the wings provide some aerodynamic forces to that to keep it going up. Well, what about in space? They don't have air. Do they have wings? No, they don't have wings. The space shuttle had wings. Yes, the space shuttle had wings, but that was for when it was coming back to Earth through the atmosphere. In space, those wings did nothing. Oh. I'm imagining Tim asking these questions for some reason. I don't know, Tim, we're picking on you today. All right, so we have the force of gravity, the aerodynamic force. Do we have any other forces? Oh, well, maybe. Well, it's a jet plane. What is a jet? It's a engine, and it's an engine that is providing a thrust. And so let's say we've got some thrust pushing the plane in that direction. Now, it's really kind of interesting. I'm going to look at this, we'll talk about this in just a minute. But we're going to have thrust that's pushing in a direction, but it's traveling at constant speed. Is this force balanced? No, there is no other force right now. The speed is balanced, or the speed is constant, the acceleration is equal to 0, the net force has to be equal to 0 as well, which means that there has to be a force going in the opposite direction. And we could call this air friction. Let's just call it friction. It's the force of friction going in the opposite direction. When you're traveling in a car, going down the highway, and you stick your hand out, you feel anything? Yeah, you feel the air rushing over you. So that air provides a lot of friction to the airplane as it's traveling. Now, because these are constant speed, this force will be equal to this force. Is it moving up and down? No, so it means this force is balanced by this force. When we take a look at the net forces, we're going to take a look at the net forces in the x and in the y and check to see whether they're balanced. If the aerodynamic force was greater than the force of gravity, the plane's going to be going up. even though these two forces are equal to each other. Or if the force of gravity is greater than the aerodynamic force, then it's going to be falling down. If the thrust force is greater than the friction force, the plane's going to be speeding up. So all of these things are happening within here, and we have to look and understand what's going on. But how does a jet engine work? So let's draw our jet plane again. Well, I'm sure not all of you may have been on a plane, but you've seen where you've got a jet engine happening, and they'll have on a big plane, they'll have sort of a shape like this, and they might have a bit of a cone back here. And what's the front? Well, this is the front. This is the back. Well, what does the jet engine do? Well, the jet engine has some things it spins on the inside, and it produces thrust. It throws the air back. Throws air. And it's throwing the air back in that direction. But hold on, the plane wants to go in that direction. Yes. Yes, it does. So as it throws the air back in this direction, the motor, which is attached to the airplane, pushes the airplane in that direction. This is sort of Newton's third law for every action. So this would be the action part. The jet engine is throwing the air backwards, and the reaction part is the plane moving forwards. I mean, the same thing is true with a rocket. So if we've got, there's my rocket, and here's my rocket here. Well, how does the rocket work? Well, the rocket produces some flamage, and a lot of flamage, which means that it's throwing hot gases down. There's a force that's going on, but the rocket goes upwards, and that's because there's a reactive force. Let's just call it Fr. There's a reactive force to that causes it to go up. So what we want to do, goes beyond what we're doing right now. Well, yeah, we want to be moving the mass. We want to be moving the mass. We want to be moving the air quickly. And when we do that, we get greater force. All right, so just some talking. So we have a jet engine. Here another one. So a woman is pushing a refrigerator at 20 centimeters per second. If she's pushing with a force of 400 newtons to keep it moving, what is the force of friction light? Is it more, less, or equal to 400 newtons? The correct answer, equal to 400 newtons. But let's just talk about it. First of all, let's draw a refrigerator. And so what are the forces acting on the refrigerator? Well, there's going to be a force of gravity. Well, that's the first answer is the correct answer. We've got the force of gravity. We're going to have a reactive force going up. Is the refrigerator moving down or moving up? Probably neither. Nothing of that's happening. What type of force does this come? Well, this is a normal force. Why? Because it's perpendicular to the surface. So we have a force of gravity over normal force, and these forces are going to be equal to each other. And if those forces are equal to each other, we add them up, the net force would be equal to 0, and so the acceleration is equal to 0, or the mass has to be equal to 0. That doesn't make any sense. So what is she doing? Well, she's pushing. And there's a force of a push. And as she's pushing with a force that's equal to 400 newtons. Now, is there an acceleration? And the acceleration is equal to 0 meters per second squared. How do we know this? Because we're told that there is a velocity of 20 centimeters per second. And if there's just a velocity and that's not changing, then the acceleration has to be equal to 0. So if she's pushing with 400 newtons, there has to be a force of friction that's equal to that of 400 newtons. If she pushed with a force of 402 newtons, and this was force of friction was 400 newtons, then we would have a net force of 2 newtons, and there would be an acceleration. It just might be small. All right, going on. We've got a 1,200 kilogram boat, and it's accelerating at so many meters per second squared in a straight line. Are the forces balanced or unbalanced? Is your friend balanced or unbalanced? How much fun. All right, so if we're having, what we're going to have is we're going to have it unbalanced. This is the correct answer. It's going to be the correct answer because it's accelerating. Newton's second law, F net is equal to ma. If this is not equal to 0, then this can't be equal to 0 either. The only way the net force can be equal to 0 if the mass is equal to 0, and that doesn't make any sense. All right, so what we've got, so let's draw our boat. There's our boat. What forces do we have? Well, we have the force of gravity. Excellent. Do we have an upwards force balancing it? Yes. And that's going to be a buoyant force because why? It's a boat and it's floating. Is it a normal force? No, it's not a surface as such. It's just still going upwards. Are these going to be equal to each other? Yes, because the boat is not sinking, we hope, and it's not flying up into the ground, so these things are going to be equal to each other. So it's accelerating. And so if it's accelerating, we're going to have force of motor pushing it in that direction. And if the motor force is pushing that direction and we have an acceleration that's not equal to 0 and the acceleration is not equal to 0, our net force is not equal to 0. So we have a force of our motor. Is there going to be anything working against it? Yes, sure, you betcha. We're going to have a force of friction. The force of friction comes from moving through the water. You tried running on land and then try running on water. What's easier to run through? On land, through the air. Get into water, and it's hard to push. So these are not equal to each other. Those are unequal, and the force of the motor is going to be greater than the force of friction because we have this acceleration. That's a pretty small acceleration, not a lot of difference between these, but there's an acceleration. All right, let's continue on. All right, so here we're getting into sort of perhaps less conceptual, into some calculations. So if the net force on a 5-kilogram bowling ball is 20 newtons, what is the acceleration? All right, so what do we have? We have talking about net force, and the net force is equal to 20 newtons. And then we have this 5 kilograms, and 5 kilograms, well, that's a mass. And what are they asking for? They're asking for an acceleration. Whoa, there we go. F net is equal to ma. F is equal to ma. Our net force is equal to 20 newtons. Our mass is equal to 5.0 kilograms. What's A equal to? Well, A will be equal to 20 divided by 5, and that's going to be equal to 4 meters per second squared. There we go. Let's put our vector signs on top of those things, because those are vectors. Mass is not a vector. I'm getting fat in a certain direction. No, it doesn't work that way. All right, here we have a baseball. A baseball is hit with a force of 1,000 newtons and accelerates at 4 times 10 to the 3 meters per second squared. What is the mass of the ball? All right, so what do we know? We have 1,000. 1,000 what? 1,000 newtons. So what do we measure in newtons? Force. When do we want it? Now. What do we measure in newtons? Force. What? Sorry. I really don't know what you guys think of these things. Yeah, let's just leave it there. So we have this 4 times 10 to the 3 meters per second squared. What is this? It's our acceleration. And then what are we left with? Mass. And that's what our question is. Because we have this, F net is equal to ma. I didn't always used to write F net. I would just write F. But really, it will make more sense when we talk about this as the F net. So we're going to start adding more than just one unbalanced force into this thing. All right, so then we've got our 1,000 newtons is equal to our mass times 4.0 times 10 to the third meters per second squared, substituting in. So then our mass is going to be 1,000 divided by 4 times 10 to the third. I have to pull out my Casio FX260 Solar for this one. 4, no, 1,000 divided by 4, 10 to the third equals, woo, you ready? Are you? That doesn't sound right because I'm getting an answer of 0.25. And I think I just did something wrong. Oh, right, because what is the mass? 0.25. I just thought I was calculating acceleration. This is a kilograms, so 0.25 kilograms. What's the mass? Sir, what are you doing? I don't know, I'm slacking off. It's the COVID-19. I don't know. It's our mass. 0.25 kilograms. I tried to get a new computer on the weekend. I couldn't do it. Couldn't meet up with the person. It didn't work. Anyways, different story. We'll keep you informed. Still waiting, faster internet. Still waiting. Didn't come on Friday. Hope it comes soon. All right, here we have another question. What unbalanced force is needed to accelerate a 3 times 10 to the 4th spacecraft at 2.5 meters per second squared? So we have these numbers. 3.0 times 10 to the 4 kilograms. Well, what is that? We'll measure it in kilograms. That's a mass. Then we have this 2.5 meters per second squared. Well, what is that? With that unit, that's an acceleration. And what are we asking us to find? We're asking us to find the net force. All right, so let's just put these things in. So our net force, well, that's going to be equal to our mass times our acceleration. 3.0 times 10 to the 4th times 2.5. I didn't put my units in. Sorry. 3 10 to the 4th times 2.5 equals 75000 newtons. Woo, woo, woo. And that would be our net force. That would be the force that is accelerating the spacecraft. Dun, dun, dun. Here we have a slightly different question. Well, they're always different, but here we have we're adding some complexity to this. How much force is needed to accelerate a 2 kilogram block at 4 meters per second squared where there's this friction? All right, so let's take a look. Let's take a look. So we have 2.0 kilograms. What is that? That's our mass. We have this 4.0 times meters per second squared. Well, what's that? That's an acceleration. And then we have this 10 newtons. What's that? That's a force. Hold on, what's going on? What's our question? Well, this is a force of friction. And we're saying how much force is needed to accelerate. So we're still looking for a net force. Okay, so let's draw a diagram. What are the forces acting on this? Well, we've got the force of gravity. We've got a normal force. We've got a force of friction. And so then we're going to need to have a force of a push. Is the force of the push going to equal the force of friction? No. Why not? Because it's accelerating. The acceleration is not equal to 0. So our net force is not equal to 0. Because these are going in opposite directions. So how much force do we need to put in? Well, here's the thing. Here we have force of our push. We need to have a net force that is large enough so that when we add I got this wrong. The diagram is going to look similar. Our net force is the accelerating force. This is our force net. And our force net is going to be equal to, well, what forces? We're going to have the force of our push plus the force of our friction. So there's our net force. In essence, this is our resultant because that's what we're adding up. So how do we get that resultant? Well, we have to have a force of a push that is greater because we have this force of friction that we're adding to it. This plus this is going to be our net force. We're going to have a net force, or we're going to have a force of a push that is greater than what our net force is. The thing is that we can calculate what the net force is. We can calculate, so we can use our F net is equal to MA. Our mass is 2 kilograms. And our acceleration is 4.0 meters per second squared. And when we do that calculation, I think I can do that in my head. 2 times 4, that's equal to 8 newtons. That's our net force. That's the net force that is our mass times our acceleration. But our force of our push plus our force of friction has to equal 8 newtons. Our force of our push plus our negative 10 newtons has to equal 8 newtons. Why is this negative? Because it's going the opposite direction. If we were to go back up top here, then we would say that this direction is positive. And we can say upwards is positive as well, but upwards and they're equal to each other. So they cancel each other out. Those two forces, one line. Anyways, and these are unequal. So we're going to have force of the push is 10 is equal to that. And then we do our easy peasy mathematics. That's going to be 8.0 plus 10, and that's equal to 18 newtons. So the force of the push has to be 18 newtons because we're overcoming 10 newtons of frictional force so that it accelerates with a force of 8 newtons. Most of the time, we would sort of know the force of the push that we're measuring, well, or that we're doing, and the force of friction. We add them up together, we come up with our 8 and figure out the acceleration. But this is a different sort of question. It's good question, because it really brings up, this is the key thing. Our net force is the sum of our forces, and we need to make sure we know the directions are positive and set these things up and recognize we're going to have a positive and a negative when we're adding them together. All right. So here we have, so there were some questions with F equals ma, the second law. Here's some questions. This actually corresponds to question number 1 in the review that you're going to be doing today. And what we're being asked is, what is the reaction force in each of the following cases? Well, a canoe paddle pushes on water, excuse me, with a force of 150 newtons east. I'm actually going to draw a paddle. What goes through my mind is land of the silver birch, home of the beaver. Worked at a camp for a couple summers, did a lot of canoeing. You learn how to handle a canoe, and there's actually ways to handle a canoe properly and safely, and can be quite efficient and useful to use. But when you have a canoe and you have a paddle, well, what do you do with the paddle? You put it into the water and you push against the water. And when you push against the water, you're sort of pushing yourself forward against the paddle. And so your arms are pulling on the paddle and you're pushing yourself forward. So if the force is 150 newtons and it's east, the reactive force will be 150 newtons west, and the square brackets. There's the reactive forces. Forces come in pairs. By applying a force to the water, we're getting a force that's moving us forward. Now, is this going to be exactly 150 newtons? No, because if you ever, excuse me, took a look at the paddle when it's in the water and you're pushing the paddle in this direction, the water is flowing and it's swirling around this as you're pushing the paddle, because the paddle's also moving through the water. If you were pushing off on rock, well, the rock's not moving, and so you wouldn't have 150 newtons pushing off a rock gives you 150 newtons pushing forward. But if you're pushing with a paddle against the water's going to flow and it's going to use up some of that force. Just saying. A bulldozer pushes a large rock with 10 to the fourth newtons at 0.2 meters per second squared. I'm sorry, I just want to draw a bulldozer. Oh. There's the tracks, then you've got the front of the bulldozer, and you've got the smokestack. You've got the person who's driving. Anyways, they're pushing a big rock. And they're pushing it in this direction. And they're using a force of 10. Well, okay, so, and it's accelerating. The acceleration is not equal to 0, which means our net force is not equal to 0. So if we have our rock, let's do this properly, draw a nice picture of the rock. We're going to have our force of gravity going down. We're going to have a normal force going up. Those two forces are going to be equal and opposite and balanced because it's not flying up into the air and it's not digging into the ground. So those are going to be equal and balanced as the net force up and down will be there. We're having the force of a push. And the push is 10 to the fourth newtons. So 10,000 newtons. Are there any forces that is acting other forces? Sure. Because if we're pushing with 10 to the fourth, we're only accelerating at 0.2, pretty piddly, which means there has to be a pretty big force of friction as well. Now, this will not be equal to that. They are not going to be equal. The force that pushes greater. How do we know? Because there's an acceleration. There has to be a net force in this direction, in this case. Net force in that direction will have a non-zero acceleration, and we're all good. So, we're talking about reactive forces. If we consider I just want to make sure I'm giving you the right answers to these things. When you start talking about forces and talk about the direction of forces, what is the reaction force in each of the following cases? All right. So the reactive force, well, we have to understand, let's come back to here. So we have a force of a push in this direction. Let's get rid of the net force, talking about that. And that's going to be equal to 10 to the fourth newtons. Is there a reactive force? Sure there is. The rock is pushing against the bulldozer. We're talking about this situation up here. How does that correspond? Well, that's going to be less than 10 to the fourth. How do we know? So this is our reactive, that looks like 40. That's not what I meant to say. So we have a force of a push this way. We're going to have a reactive force. This force is going to be less than 10 to the fourth newtons. And that's because we have a net force in this direction, because we have an acceleration that's not equal to 0. So this force and this force are not equal to each other. All right. A baseball hits a window with a maximum force of 400 newtons south and breaks it. Actually, sorry, we should go back to to this one. So we are pushing in which direction? West, and so there would be a reactive force that is east. So I got the drawing is backwards, but the reactive force would be east, not the net force, but the reactive force. All right, a baseball hits a window with a force of 400 newtons. Sorry, I should draw that like a baseball. So here's our window. You'll see what I mean. Let's get rid of this. Okay, here's our window. Here's our baseball. All right, what forces are acting on this? Well, we have a force of gravity. Is there a normal force? No. No, because the normal force would be going in this direction. There's the surface. Is there a force of friction? Well, is there any other forces acting on this that would be going upwards? Well, you're going to have a certain amount of force of friction. You're going to have force of gravity pulling it down. It's accelerating downwards, actually. So in terms of vertically, there's an acceleration. What's that acceleration equal to? 9.8 meters per second squared. Kind of subtle there. Kind of subtle there. So it's falling. Because, so it's going, and it's coming back down, and it hits the window. And when it hits the window, it applies a force of 400 newtons. Is there a normal force? Yeah, you betcha. Here's our force normal. Don't normal forces go up and down? Normal forces are perpendicular to the surface. The window's the surface. There's a normal force. Our normal force is going to be less than 400 newtons. How do we know that? Because the window breaks. This force is greater than the strength of the window, and the window breaks. Bad time for Billy. Have glass insurance. All right, and finally this comes to D. We've got the wheels on a car go round and round, and they push on the road with a force of 250 newtons south, and there's a force of 2,500 newtons down. All right, so we've got 2,500 newtons down. What's the reactive force? Well, is it moving into the ground? Is it flying up into the air? No. Then our reactive force is 2,500 newtons up. And that's going to be a normal force because it's a surface, horizontal. And this is going to be our force of gravity. So we have those. But then we've got this 250 newtons south. So I'm saying this direction is south. And so the wheels are pushing with 250 newtons south. Well, there has to be 250 newtons north. And that would be our reactive force. Because you got your car, and you got your cars on the road, and the car wheel spins in this direction. Why does it spin in that direction? Because there's friction in here, and it pushes back on the road that way, so that the car travels in that direction. You want to go forward, you're always pushing backwards, and it goes forward. Think about this when you get up to take a walk and go get a glass of milk. Here you are. There's your shoe. And your shoe, oh, it's a nice shoe. Let's put some laces. And you've got your ankle and your calf. Well, anyway, you're walking. What is your shoe doing? Well, your shoe is pushing backwards that way. Why does your shoe push you backwards that way? Because you're traveling, trying to go that way. How do we know that this works? Well, think of the last time that you wore hockey skates. And hockey skates, this looks really bad, but hockey skates look like this. And you ever try to walk on hockey skates? You move your foot backwards, but there's no force of friction, so your foot goes backwards. And what do? Nothing, and you fall. How do you skate with hockey skates? Well, if you think about it, with hockey skates, if you're a girl and you're using figure skates, then your states have picks at the end, and your blades have picks at the end. and then you use those, and you dig your picks in to the ground, and you push that way so that you push yourself that way. But if you're playing using hockey skates, then what you do is that you turn your foot at a bit of an angle. And when you turn your foot, you apply a force in that direction. And so if we were to take a look at the blade is sharpened. And so this edge digs into the ice. And so you're pushing in this direction and you're getting a reactive force in the opposite direction. So you push that direction and you move off in this direction. But you want to go this way. That's why you got your other foot. And you're pushing in this direction and you're moving off in this direction. So you go left, left, right, and that gets you moving forward. Cross-country skiing, you do the same thing. There's skate skiing. It's like this, and you're pushing sideways on here and you're going forward. All right. Hopefully this has made a bit of sense for you. So here we are, some questions, 6.8 review and questions 2 to 9. We did question number 1 already. Question number 2 just has you thinking about some things, and then there's some calculations you're doing. Starting with number 4, F equals ma, and then just going through. Question number 9, you've got some friction coming in, and you have to sort of think about this. And so we'll have another lesson. Probably give you 2 days to work on this. Another lesson Wednesday. We'll see how this goes. Again, let me know how things are doing. We're going at an okay rate. Are we going to get through all that we would normally get through? No, that's fine. But we're going to get the important things. Here we are talking about Newton's laws. Newton's law is very fundamental. I want to get on to coupled systems within Newton's law as well. Just coupled systems are fun, because you're figuring out these different things in different directions. Chapter 7 is talking about momentum. I know you don't have that book. Momentum is really, really an important concept. People talk about momentum all the time, and they talk momentum, but they're really using it in a wrong way. And chapter 8 is work, energy, and power. And with momentum, you have conservation of momentum. And then we work, energy, and power. We've got conservation of energy as well, and really, really important that comes into there. And we'll see how things go. And there, so we're going to get through that stuff, and that stuff is really, really rather core. I'm not sure if we'll do any electricity. Sometimes we don't get to that. Electricity can be good. Electricity is so important. It's around us all the time. We use it for doing so much for us. And Physics 12 don't always get to it as well either. But what's really important as well is, there's magnetism. So I'm just leaping through some things. Radiation we won't do really, but we did some of that in chemistry. But waves are incredibly important. Incredibly important when it comes to sound, when it comes to light, when it comes to all sorts of things out there. And talk about vibrations, vibrations in your car and different things like that. And I'm just taking a look at this book, and as it talks about waves, and then it talks about sound and light and lenses and things like that. We're talking about going from color that comes into this, and the nature of light. James Clerk Maxwell, which I've never really understood, but I know he did lots of light. Well, so. Talking about waves. Waves starts in this book, chapter 18. And it goes through to chapter 26, almost 10 chapters dealing with waves and the practical applications of waves and light and sound and so on. So we'll see where we get. We got a lot of good stuff coming up. And hey, I'm glad you guys are part of Physics 11. And This is a really strange year, but I'm really pleased to have been teaching you guys. Yeah, even you, Ty, even you. Because there's always going to be one who's going to start questioning us, or you're not meeting me. Anyways, no, I'm really, I enjoy you guys and wish you all the best. Anyways, here we go. I'm talking too long and then blabbed at the end. And here I am trying to be a YouTuber. I got to get better than that. All right, take care, guys. And when you got questions, come on and ask. That's the way it goes. All right.